Okay, here is what we are doing today, Wednesday, December 2nd. Go to Haiku, on our chemistry page, pull up the link for negativities. You need to add those to your periodic table so that when we go through these problems and for the test, you have electronegativities. Next, you're going to finish Lab 8, and I'm going to go through some of that right now. That will be due tomorrow, Thursday. And remember, your test over chemical bonding is tomorrow. Make your card. Okay, let's move on here. This is the table. These are two of the things on the table that you're going to finish in the lab, and I'm going to show you how to do it. So the process of drawing a Lewis structure we've been doing many times, right? And the process is start by counting the total valence electrons. Okay, sulfur has 6. Fluorine each has 7, and I have 2 of those. So I have 14, right, plus 6 is 20. So let's start our Lewis structure. That will be the middle. Let's see what I have here. All right. I have used so far 2 bonds or 4 electrons. I'm left with 16. Well, let's see. I'm going to put an octet on my fluorine because they need their octets, right? So I've used 2, 4, 6, 8, 10, 12. That leaves me 4, doesn't it? Well, I have 4 that I can put around sulfur. Now notice that we have used all the electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Fluorine has an octet, fluorine over here has an octet, and sulfur has an octet. Now sulfur can sometimes take more than an octet. In this case, it's taking an octet. All right, so let's talk about around the central atom, which is here. We have 2 bonds going on, right? So I have two bonding pairs, and I have 2 lone pairs for a total of 4. When you go to your geometry sheet, you look up 4 total electron groups around that central atom, 2 lone pairs. You end up with a bent geometry, which looks like this. Right? And then really they show the lone pairs sitting up here on top of the sulfur. The bond angle's right off the sheet. Now let's talk about if this has a dipole. To consider dipoles, right, we need to see the electronegativity differences between these 2 atoms. Sulfur's electronegativity is about 2.5. Fluorine's is about 4.0. Well, that difference, gosh, is 1.5. So we definitely have polar covalent bonds here. So what we'll see is fluorine's more electronegative, right? These electrons are being pulled toward the fluorine, away from the sulfur. The way this is drawn, you see the fluorines are toward one side of this molecule, the sulfur's toward the other side. Because the electrons are being pulled toward the fluorine, this is our partial negative side, and this is our partial positive side. So this does have a dipole. Okay? Let's look at PBr3. Count valence electrons. Phosphorus has 5. Bromine has 7 times 3, 21. So 21 and 5 is 26. So we have 26 valence electrons. Let's lay out our possible possible layout. Phosphorus is our central atom. I've used 2, 4, 6 electrons so far, and I have 20 left. Well, I start by filling the octets around the bromine, right? I just added 6 to each bromine. That's 18. I'm left with 2. Well, that's good because while the bromines are happy, phosphorus needs 2 more electrons to have an octet around it, right? So this has used all our electrons. Everybody has an octet, so this looks like what we have. So we have, looks like 3 bonding sets of electrons, 1 lone pair for a total of 4. So if you move to your geometry sheet, you look up at 4 electron sets, 1 lone pair, and you find that your geometry is trigonal pyramid. And it looks like this. I'm trying to draw a dimension here, folks. That's what those are in this lone pair. Remember, we described this as a camera sitting on a tripod, right? 3-legged tripod. So here's our phosphorus, and our bromines are at the end of that tripod. Let's now consider if PBr3 has a dipole. So we talk about, again, the difference in electronegativities. Bromine has a 2.8. Phosphorus has a 2.1. Wow, we are just over our bogey of 0.6. So these bonds are slightly polar covalent, pulling toward the bromine, right? So if the electrons are pulling toward the bromine and the molecule looks like this end of it that has the bromine is going to be partially negative. This end up here that has the phosphorus will be partially positive. So both of these atoms have a dipole. Now, while they weren't asking for it in this lab, we need to be able to decide if something has a dipole. Okay, let's move on. I want to review some of the things on homework 11. Okay? We're going to do basically the same thing we just did on that prior page. Excuse me, we're going to start with the Lewis structure. So I need to know valence electrons for silicon. I have 1, 2, 3, 4. Fluorine has 7. 7 times 4. So 28 and 4 is 32. So let's lay this out. Now, these 4 bonds are 8 electrons. I've just used 8. So I'm left with 24. Well, each fluorine gets 6 to finish the octet, right? 6 times 4 is 24. I've used up all of them. Now let's see, is everybody happy? Yes, fluorines are happy, and the silicon has an octet. So if we go to our geometry page, we have 1, 2, 3, 4 sets of electrons, 0 bonding pairs. So our geometry is tetrahedral. Let's go back to our analogy about the camera. So silicon sits in the middle. We have the 3 of the fluorines coming out in a tripod below, and 1 fluorine sitting here. Let's look at the electronegativities. Fluorine is 4.0, silicon is 1.8. Each of these bonds between silicon and fluorine are definitely polar covalent. But we're going to see, let's look at the geometry now. So if I have this silicon, I got fluorine pulling here, fluorine pulling here, here, and here. This molecule is completely symmetrical. The silicon's in the middle, the fluorines are equidistant from each other around the outside. That's what tetrahedral does for us, with bond angles of 109.5 degrees. Because the fluorines are pulling symmetrically out from the silicon, when they pull the electrons away, the other fluorines pulling the electrons away cancel out any dipole on the molecule. So there is no dipole on this molecule, even though each bond itself is polar covalent. Okay? All right, let's look at BH3. All right, so we're going to look at this BH3. One thing I want to show you, though, is in our lab, I go to the page I'm looking for here. I want to review the exceptions to the octet rule. There are compounds that can be exceptions to the octet rule. Boron is one of them. it can take less than 8, while phosphorus, sulfur, and xenon can take more than 8 if needed. All right? So let's go back and look at this. Let's count our valence electrons. Boron has 1, 2, 3, and then I have hydrogen, which each gives me 3. So I have 6 electrons. That's not much, is it? Well, if I lay this out, I have used all 6 of my electrons. I have none others. So if boron needed an octet, I couldn't give it to it, could I? So we know that boron can be an exception, and you need to write those exceptions on your card. Boron can be an exception, and this should be a happy Lewis structure. So notice, let's do the geometry. We have 3 sets of electrons around that central atom. So go to your page and look at 3 in the first column, 0 lone pairs, and you come up with trigonal planar, which has bond angles of 120 degrees. Now, here again, if boron has 2.0 electronegativity, hydrogen has a 2.1. Those are basically non-polar covalent bonds. There's no dipole on this molecule. Okay? So here, because of the difference is so small, it's 0.1, these bonds are non-polar covalent. The molecule does not have a dipole. All right? Now, let's look at some ions here. Let's look at this one. So I will look at valence electrons. Sulfur has 6. Oxygen each has 6. What do I do with this 2-? Well, that means this ion gained 2 electrons, didn't it? So I have 6, 18, and 2 for 26. Let's lay this out. Sulfur, oxygen, oxygen, oxygen. All right. So I just used 6 of these to bond those together. I have 20 left. Well, I'm going to fill my octets around the oxygens, right? 6 times 3 is 18, minus 18 leaves me 2, which I believe will be right there on our sulfur, our central atom. Okay, let's make sure 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. And that's right, 18, 20, 26. Okay, so let's look at the geometry of this ion. And remember, if I'm drawing this Lewis structure, and it's an ion, I need to write it like this. The brackets and the charge need to be on it. So we have 1, 2, 3, 4 sets of electrons around the sulfur. So you would go to your geometry page and look at 4 total sets of electrons, 1 lone pair, and this will give you the trigonal pyramid, which is our camera with the oxygens coming out in the tripod as the tripod, with the lone pair sitting up here. Now, let's consider electronegativity. Sulfur is 2.5, oxygen is 3.5. Well, that's a difference, right, of 1. These are definitely polar covalent bonds, pulling toward the oxygen, right? Pulling toward the oxygen. So if you look at this ion, well, it has an overall charge of 2-, which really is going to be, it's going to be a minus ion overall and be involved in ionic bonding, right? But if we had to consider a dipole, we would find that this is the partially negative side and this is the partially positive side. Since it's an ion, we really aren't going to worry about that too much, but I want you to be able to follow the process, okay? Now, let's look at the next one, ClO3-. It's countervalence electrons. Chlorine has 7. O each has 6. 6 times 3 is 18. And that minus means we have 1 additional, don't we? So we have 26. Let's lay this baby out.